So, as an example, suppose that we were going into the laboratory to measure a reaction that converts one substance, say substance A, into another substance, say substance B. So reactant A reacts and transforms into product B. In the laboratory, the most practical means we have of measuring quantities is often mass. Instead of determining numbers of moles directly, we're often given mass as starting information. But in order to convert between quantity of reactant A and quantity of product B, we really need moles. The scheme that will follow when we're given information about mass of substances is to use the molar mass or molecular weight of a material to move from the mass of that material into number of moles. Once we have number of moles of a substance, we can use the coefficients of a balanced chemical reaction to convert from moles of that substance into moles of another substance we might be interested in. Once we have moles of a substance that we're interested in, we can use its molar mass or molecular weight to determine its mass if needed. Let's do a specific example where we have real chemical substances. Suppose that we're synthesizing sodium chloride from the elements sodium and chlorine. In the balanced chemical reaction that represents this synthesis, 2 sodium atoms react with 1 chlorine molecule to form 2 sodium chloride formula units. Or 2 moles worth of sodium react with 1 mole worth of chlorine to form 2 moles worth of sodium chloride. Suppose that we start a reaction with 15 grams worth of chlorine and allow that chlorine to fully react with so much sodium that we'll never have to worry about depleting that sodium. In chemistry parlance, we say that sodium is an excess reactant in that case. We want to be able to predict what mass of sodium chloride will form when we react all of that chlorine out. So, we're starting with mass of chlorine. The best we can do from mass is convert into moles. Remember, when in doubt, convert to moles. It's only once we have moles of chlorine that we can take advantage of our chemical reaction up above. So we're going to have to take a series of 3 conversion steps. One that moves us from given starting mass of chlorine into number of moles of chlorine. Once we have moles of chlorine, we can use our balanced reaction to convert that into number of moles of sodium chloride, the thing that we're interested in here. Given number of moles of sodium chloride, then, we can figure out from its molar mass or molecular weight the mass of sodium chloride produced. So we're going to need a couple of things. We're going to need the molar mass of chlorine and the molar mass of sodium chloride to accomplish this. Chlorine's molar mass is 35.45 times 2. 70.90 grams per mole. Sodium chloride's molar mass is 23 plus 35.45, 58.45 grams per mole. So, let's begin our conversion. We have several steps to work through. Our starting value is 15 grams. 15 grams of chlorine. According to our flow chart up above, the first thing that we need to do is convert grams into moles. So we need to get rid of grams of chlorine and move into moles of chlorine. Once we have moles of chlorine, the next thing we need to do is convert moles of chlorine into moles of another substance, in this case, sodium chloride. Once we have moles of sodium chloride, our final step is to convert moles of NaCl into grams of NaCl. With all of these conversion factors in place, we'll be able to get rid of grams of chlorine, moles of chlorine, moles of NaCl and be left with just grams of NaCl at the end, the thing that we really wanted to know about. Now we have to fill in these conversion factors. To fill in this one, we need the molar mass of chlorine. 1 mole worth of chlorine has a mass of 70.90 grams. And for the final conversion factor over here, we need the molar mass of sodium chloride. 1 mole worth of sodium chloride has a mass of 58.45 grams. That was the work we did as preliminary tasks, figuring out the molar mass of chlorine and NaCl respectively. For the conversion factor in the middle, though, we can just use coefficients from our balanced chemical equation to fill in directly. The coefficient in front of NaCl up above is 2, and the coefficient in front of chlorine is 1. Thus, we have all of these conversion factors assigned values, and we can move through our calculation directly. 15.0 divided by 70.9, multiplied by 2, multiplied by 58.45. We'll keep 3 significant digits at the end because our starting value has 3 sig figs, and these are exact numbers. Our final result, then, to 3 sig figs should be 24.8 grams worth of NaCl. We can expect to produce this much sodium chloride from reacting fully 15 grams worth of chlorine. Notice that this is not double the mass of chlorine. We started with 15 grams worth of chlorine. We do not produce double the mass of sodium chloride. And that's because masses are not directly comparable for 2 different things. The mass of a chicken egg and the mass of an ostrich egg are significantly different. The mass of a chlorine molecule and the mass of a sodium chloride molecule are significantly different. It's only numbers of moles, or total quantity, that are directly comparable. So let's do a second example. Let's suppose that we want to be pragmatic and only use as much sodium for this reaction as needed, so that we don't have to waste any excess. What mass of sodium would be required to fully react away 15 grams worth of chlorine? See if you can figure this out. Pause this video, then come back for the solution when you're done attempting this problem. So we're going to set this up very similarly to how we set up the first example. We have a starting amount of chlorine in grams, but we can't move directly from grams of chlorine into grams of sodium. We have to first, when in doubt, convert to moles. So we've got to get this grams of chlorine to moles of chlorine somehow. The first thing I'm going to do is divide by the molar mass of chlorine to accomplish that. And then, once I have moles of chlorine, I can move from moles of chlorine into moles of anything else in a balanced chemical reaction. In this case, it's sodium rather than sodium chloride. Lastly, once we have moles of sodium, we can move from moles of Na into grams of Na, given the molar mass of sodium. To fill in these conversion factors, we need a molar mass here. The molar mass of chlorine we determined earlier as 70.90 grams per every 1 mole. To fill in the second conversion factor, we need a balanced reaction. Moles of one substance, sodium, is 2 according to our balanced equation. Moles of the other substance, chlorine, is 1. Lastly, to go from moles back into grams, we need a molar mass once more, this time for just sodium. According to the periodic table, that's 23 grams per mole. We'll get rid of grams of chlorine, moles of sodium, and be left with grams of sodium at the end of this calculation. Once more, we'll keep 3 significant digits, and when we do, we should end up with 9.75 grams worth of Na. For a final example, let's think about how much, in terms of mass, sodium chloride is produced if 15 grams of chlorine are mixed with 15 grams worth of sodium. Here we're given starting amounts of two of our reactants. We're going to mix 15 grams of each one together. So, how do we solve this problem? It's like we're given two starting values. We've already figured out what mass of sodium chloride could be produced from 15 grams worth of chlorine. Let me bring that back up. So we showed a few minutes ago that from 15 grams worth of chlorine, we would expect 24.8 grams worth of sodium chloride. What would happen if instead of 15 grams worth of chlorine, we'd reacted 15 grams worth of sodium? What if we used our other starting value instead? 15 grams worth of sodium would have to be converted to grams worth of sodium chloride using the same process as above, except everywhere we see Cl2, we're going to replace with Na. We'll go from grams of Na into moles of Na, from moles of Na into moles of NaCl, and from moles of NaCl into grams of NaCl. And what we end up with will be an alternative solution in grams of NaCl. Our coefficients will be built in as follows. 1 mole of sodium has a molar mass of 23 grams per mole. The coefficient in front of sodium chloride in the reaction is 2. The coefficient in front of Na is 2. Our molar mass of sodium chloride is unchanged. It's still 58.45 grams per mole. When we carry through this calculation and keep 3 significant figures, we end up with a result that shows us 38.1 grams worth of sodium chloride would be produced. So if we reacted 15 grams worth of chlorine, we'd make 24.8 grams worth of NaCl. If we react 15 grams worth of sodium, we'd make 38.1 grams worth of NaCl. So what's the true answer here? Are they both right? How could they both be right? If we mix together 15 grams worth of one ingredient with 15 grams worth of another ingredient, how could we expect to get two different results? Well, they can't both be right. So which one is the correct one? It might stand to reason intuitively for you that the smaller amount is the more correct one. Why is that? In the next video, we'll learn that the answer deals with limiting reactants and the nature of the thing that runs out first in a chemical reaction.